Section 8 of Easy Lessons in Einstein. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Easy Lessons in Einstein by Edwin E. Slauson. Section 8. The Eclipse Observations. In the history of science, the year 1919 is likely to be known not as the year of the overthrow of the German Empire, but as the year of the overflow of Newton's law of gravitation. The British astronomers who went to Africa to observe the eclipse of the sun May 29, 1919, came back with the proof that a ray of light passing close by the sun is bent out of its straight course. The photographs taken during the 6 minutes when the sun was shadowed show the surrounding stars in different positions from where they are seen when the sun's disk is not in their midst. This is the second time that Einstein has scored over Newton. The first was in regard to the orbit of Mercury. If the sun and Mercury were alone in the universe, the planet, according to Newton's law, would revolve forever around the sun in the same elliptical track. But the presence of the other planets makes Mercury deviate from this regular route, so the ellipse it describes is never quite the same, but slowly drifts around, so that in the course of centuries its longer diameter would be pointing in a different direction. Calculating by Newton's law, the influence exerted by the other planets, astronomers found that it would shift the orbit of Mercury 532 seconds of arc in a century. But when they took observations on Mercury, they found its orbit was shifting at the rate of 574 seconds. The discrepancy between observation and theory, 42 seconds, is 30 times greater than could be accounted for by errors of instruments or observation. But according to Einstein's theory, if the Sun and Mercury were alone in space with no other planets interfering, the orbit of Mercury would not remain the same, but would advance at the rate of 43 seconds a century. This, as the reader will observe, is in substantial agreement with the discrepancy which has for 2 centuries puzzled astronomers, since it was inexplicable on the Newtonian theory. The electromagnetic theory of light, thought out by Clerk Maxwell 45 years ago, has proved to be an excellent guide to research and led to many practical applications, such as wireless telegraphy. According to this theory, the miles-long Marconi waves, the infinitesimal waves that we feel as heat or see as light, and the still more minute waves of the X-rays are movements of the same sort, though differing in length, and all travel at the same speed in space of 186,000 miles a second. It was one of the implications of Maxwell's theory, though it was not perceived until later, that light and all such waves must exercise a certain pressure upon a body against which they strike, just as a jet of water from a fireman's hose pushes against the side of a house. The pressure of light is so exceedingly slight that it had never been noticed, but it has been actually detected and measured by Professors E. F. Nichols of Yale and G. F. Hull of Dartmouth. The sunshine falls upon the earth with a force of 160 tons. Both theory and experiment have shown that a beam of light has inertia or mass, that is to say, a beam of light pushes like a water jet, and it has now been proved by the eclipse expedition that the pull of gravity deflects a beam of light as it does a water jet. That is to say, a beam of light has weight, is attracted by gravity. This deflection of a beam of light by gravity is extremely small, but photographs taken during the recent total eclipse of the sun shows that starbeams that pass near the sun are bent out of a straight path. Here is a diagram that depicts the Earth and the sun more or less in a straight line with 2 instances of a star. The following caption accompanies the diagram. the eclipse expedition found that the stars seen about the sun appear slightly shifted from the position they occupy on a map of the same region of the sky when the sun is not in their midst. This shows that a ray from a star is refracted or bent as it passes close to the sun and confirms Einstein's theory that light is affected by gravitation. The observed angle of deflection agrees closely with that predicted by Einstein, but is twice as great as that required by Newton's theory of gravitation. In this diagram, of course, the angle of the deflected ray and the size of the sun and earth relative to distance are greatly exaggerated. End of caption. A better illustration of the eclipse observation than I could word is given by Sir Oliver Lodge in his interesting article on, quote, "The New Theory of Gravitation," unquote, in the 19th century of December 1915, from which I therefore quote. Take a fine silk thread of indefinite length and stretch it straight over the surface of a smooth table or floor. Imagine a star at one end of the thread and an eye at the other, and let the thread typify one of the rays of light emitted in all directions by the star, viz., the ray emitted in the direction of the observing eye. Now take a halfpenny, or an American quarter, place it on the table close to the thread so that the eye end of the thread is 10 feet away, then push the halfpenny gently forward till it has displaced the thread the barely perceptible amount of 1/1000th of an inch. The eye looking along the thread will now see that the ray is no longer absolutely straight. In other words, the star whose apparent position is determined by that ray will appear slightly shifted. The scale is fixed by the size of the halfpenny, whose diameter, 1 inch, is used to represent the sun's diameter of 800,000 miles. The 10-foot distance between the eye and sun practically supposes that the eye is on the earth, which would be a spot 1/100th of an inch in diameter, or about the size of this full stop. As for the distance of the star, at the other far end of the thread, that does not matter in the least. But, on this scale, it may be interesting to note that one of the nearest stars, about 8 light-years away, would require the thread to be 1,000 miles long. The ray is now bent or deflected as it passes the neighborhood of the sun on its long journey, so that it is out of place 1/1000th of an inch at the distance of 10 feet, and the effect of this tilt of the ray upon the observer is to make him just able to see the star upon the sun's limb when it is really behind it, or to make him see a star slightly further off the limb or rim of the sun than it really is. The shift of 1/1000th of an inch at the distance of 10 feet corresponds to an angle of 1 3/4 seconds of arc, which is just the optical shift that actually ought to occur, according to Einstein, when a ray from a star nearly grazes the sun's limb on its way to a telescope, and this is the optical shift which we now know does occur. That may be taken as the definite result of the recent eclipse observations. The effect, both in magnitude and direction, had been predicted 4 years before on the strength of a mathematical investigation by Professor Einstein. End of quote. The images of two stars, one on each side of the sun's disk, will apparently be crowded a little apart when the sun comes between them. A star that would be just eclipsed by the edge of the sun's disk, if its rays came straight, may still be visible since the rays are curved. In other words, we can see around a corner, as every good teacher is said to do. If the sun were encircled by a ring of stars, or a nebula, like a halo, the circle of light would be contracted as it passes the sun, and would come to a focus at a place 17 times the distance of Neptune, or 47,600,000,000 miles beyond the sun. The observations made by the British expeditions during the eclipse of May 29, 1919, were not altogether satisfactory. At Principe, on account of a cloud that drifted by at an inopportune time, only a few photographs could be obtained. At Sobral, one of the object glasses gave distorted plates, but the other gave a very good series of 7 star images. These, when measured at the Greenwich Observatory, gave the following figures, which are in accordance with those calculated by Einstein's formula. Radial displacement of stars in seconds of angle. This table contains 7 pairs of numbers. The first number is as observed by the British astronomers. The second number is as predicted by Einstein. 0.20, 0.32, 0.32, 0.33, 0.56, 0.40, 0.54, 0.53, 0.84, 0.75, 0.97, 0.85, 1.02, 0.88. This is regarded by the astronomers of the British eclipse expedition as sufficiently close to confirm Einstein's law, but those who hesitate to accept so far-reaching and subversive a theory on the basis of these few minute measurements may hold their judgment in suspense until 1922, when the next solar eclipse, visible in Australia, takes place. Or possibly some means may be found to take star photographs close to the sun while shining. Our California mountain observatories may be of service in this, since they are perched above much of the dust and mist and denser air that causes strong light to irradiate and fog the photographic plate. Doubtless, too, the old photographs of earlier eclipses will now be got out to see if they contain any stars suitable for measuring. Some of the opponents of Einstein suggest that the observed deflection of the starlight may be due to a solar atmosphere that refracts the rays like our earthly air. But it is hardly probable that an enveloping atmosphere sufficiently dense and so far extending as to produce such an effect would have remained unobserved, and it is highly improbable that the density of such an atmosphere should have just the density and decrease with the distance at just the rate to produce the deflections predicted by Einstein's calculation. The discovery is rather disconcerting to astronomers, for all their calculations for the last 300 years have been based upon the assumption that light travels in straight lines at even speed through empty space, or, what is the same thing, through the ether. If now light is pulled aside by gravitation as it goes by a solid body, the rays from a distant star having to pass through the tangled throng of the Milky Way might travel a very devious route, and the star would appear to us to be located in a different place from where it really is. In fact, it is possible that a star which we see double may actually be single, but that rays starting out from it in different directions may be so deflected by passing near other stars that when they reach us they appear to come from different points of space and so appear to us as twin stars. There may, too, be dead or dark stars on the way whose existence we cannot discern and allow for. Now those of us who are not astronomers are not much concerned over a discrepancy of a few hundredths of a second in the measurement of an angle by the telescope. We do not care much where Mercury will be 5 centuries hence, for we do not know quite where it is now. If astronomers made the laws of nature instead of merely discovering them, we might be afraid that at their next Congress they might repeal Newton's law of gravitation and send us all flying off into space. But fortunately they have no such power, and even though they should all become adherents of Einstein's most revolutionary theories, Newton's laws of mechanics and Euclid's laws of geometry would remain as true as they ever were, not perhaps absolutely and universally true, as we have assumed, but sufficiently accurate for all practical purposes. Deviations from them can only become detectable when we come to consider movements as swift as light waves or electrons. How a heavy object can alter space relations may be seen from this simple illustration. Stretch a sheet of rubber over a hoop like a drum head. It is now level and flat, and if parallel lines are drawn across it in 2 directions so as to divide it up into squares like a checkerboard, all these lines are straight and equidistant, and all the squares are of equal size. A row of worms, starting in an even rank and crawling along the parallel lines across the drum head, would keep even all the way. Now lay a bullet on the center of the drum head. The rubber sags down and stretches, most in the middle, least at the edges. The parallel lines are no longer equidistant. The squares are no longer equal. The lines are no longer of the same length. If now we repeat our worm race, we shall find that those worms following lines close to the weight have to go downhill and up again, and so travel a greater distance to traverse the same number of squares than those following lines nearer the edge, which lie comparatively flat and are nearly as short as before. Consequently, the worms will be slowed up in proportion to their nearness to the center, and the row of their heads will be swung around at an angle to their former frontage. We might explain this by assuming that the worms, on seeing the bullet to one side, were drawn by their curiosity a little toward it, those nearest, of course, being drawn the most. Or, if we had got beyond this crude animistic method of explanation, we might assume that the bullet was attached to the head of each worm by an invisible lariat, which being pulled by the bullet drew the worms more or less to one side. The shorter the lariat, the stronger the pull. Or, if we had outgrown this crude mechanical method of explanation, we might assume the existence of a force in the lead which in some mysterious manner attracts the heads of the worms inversely as the square of their distance. But instead of inventing a wormhead psychology, or an invisible cord, or an incomprehensible force, is it not simpler to consider the space between, and to suppose that the lines to be traversed are lengthened in the neighborhood of the weight? Now these four successive methods of explanation have been used to account for gravitation. First, it was assumed by the ancient Babylonians and Hebrews that the sun and stars were living beings, gods or angels, moving of their own volition around the earth, or at least that each was guided in its orbit by its particular god or angel. The later Greeks of Ptolemy's time supposed the heavenly bodies to be sent in concentric crystal spheres and so revolved, I presume by somebody turning a crank behind the scenes. Then came Newton and said, let's discard the Ptolemaic spheres in all mechanical connection and assume a force of gravitation, attracting all bodies in proportion to their masses and inversely proportional to the squares of the distance separating them. Now comes Einstein and says, let's discard this hypothetical force and simply assume that the field of time and space traversed by a moving body is altered if there is another body in the vicinity. In Einstein's view, gravitation is not a force, it is a distortion of space and time in the presence of matter. A comet sweeping past the sun cannot pursue a straight course, as it could in interstellar space, but follows a curved path about the sun, which is for the comet the shortest way it can go under the circumstances. So too, a row of light waves coming from a distant star keeps an even front as they pass through empty space, but as they come close to the sun they find their paths impeded, or, we may say, stretched. Those going nearest the sun are slowed up the most, those farthest off the least. Consequently, the wave front is slewed around a bit, and the direction of the ray is slightly altered. If now light waves have difficulty getting past the sun, we should expect that they would experience like difficulty getting away from the sun. They would be slowed up a bit by its gravitational pullback. The frequency would be reduced, the interval of time between wave crests lengthened. This means, in the case of sound, lowering the pitch. Touch your finger to the turntable of your phonograph and you flat the tone. In the case of light, it means change of color toward the red. This effect, according to Einstein, should be, but has not been, observed. If Einstein's third prediction is verified, says Sir Oliver Lodge, Einstein's theory will dominate all higher physics, and the next generation of mathematical physicists will have a terrible time of it. For university courses, and for all practical purposes, we shall have the Galilean and Newtonian dynamics, but they will reign as a limited monarchy, and sooner or later the Einstein physics cannot fail to influence every intelligent man. If these complications are to come into science, we must leave them to the younger men. I hope that gravitation, now that it has begun to interact with light, will begin to give up its secrets, but in my time I must be content to get secrets out dynamically and leave transcendental methods to others. One English scientist, Thomas Case, writes to the Times to protest that it would have been in much better taste for the Royal Society to have adjourned its discussion before bringing into question the reputation of Newton, who was president of the Royal Society for the last 25 years of his life and raised the society to the acme of its fame. End of Section 8. Section 8 was recorded by Tom Crawford, November 2010.